All right, well, amazingly, we've made it to the very last lecture topic, and it's a fun one. This lecture topic it's continuing our discussion of species interactions. Last week we talked about competition. That's one type of species interaction. Now ignore my dog in the background. Like I was saying, last week we were talking about competition. It's a type of species interaction where species are competing with one another and neither species benefits from the other species being around. They're both using up resources that could be otherwise used by the other species. Now, prey-predator interactions are a little different. Not only are they among the most dramatic of species interactions, here we have some sort of python, I think it's probably a Burmese python, consuming a deer. Pretty amazing. And we see here a raptor killing and eating a songbird. So when we think about species interactions, oftentimes the first thing our mind jumps to is prey-predator interactions, just because they're so dramatic and they're so interesting. So we're going to, in this final lecture of the semester, we're going to talk about prey-predator interactions, how to model them, and how prey-predator systems can be stable or unstable. And we'll have a chance to do some hands-on modeling of prey-predator systems. And we're just going to scratch the surface because prey-predator interactions is a topic that is at the forefront of modern population ecology, and models get quite complex quite fast. And just like competition models, we see emergent properties that even with simple models, we see emergent properties of our systems when we put prey and predator species together and we parameterize that interaction. And, we see some pretty unexpected things happening. And the more complex the models are, the more unexpected the outcomes can be. All right, so let's get started. In prey-predator interactions, unlike competition, one of the species benefits from this interaction. Clearly, the predator benefits from getting that prey. They are able to consume the resources. The more prey there are, the more resources there are for the predator. So it is a positive interaction for the predator. Now, for the prey, it is not as positive because they are killed and eaten. So it's negative interaction on one end, at the prey end, and it's a positive interaction in the other end, the predator end. All right. Let's start by defining some terms. Now, this is a modeling class, so let's get into the modeling. Here is a really general way to represent prey-predator models. And I'm talking not just the simple Lotka-Volterra models, but this representation encompasses all of even the most state-of-the-art prey-predator models. Let's define some terms. V here represents the prey, and we can just make that association with V for victim. So V is the victims or the prey. We can't use P because P is reserved for the predators. So delta V means the change in the prey population size, and delta P represents the change in the predator population size. We can look at this this delta V, and that's representing the growth or decline of the victim or prey population. Now we see a familiar thing here. We see R, the intrinsic rate of population growth for the prey population, times V. And that just represents in the absence of predators. Now, if there were no predators, this whole term would be 0. In the absence of predators, the prey would be assumed to grow exponentially, right? And I put an asterisk here to represent the fact that maybe we'll include density dependence. So this RV asterisk just represents any of the population growth models that we've already talked about. So it's just a generic, population growth model. Perhaps density dependent, perhaps not. This term represents the degree to which the prey population is consumed, or the number of prey consumed per time step. And that is broken down into this F, or function of the victim abundance and the predator abundance. This function of the victim abundance and predator abundance is often called the functional response. It's the per capita rate of prey consumption, or the per predator rate of prey consumption. And then you just multiply that by the number of predators to get the total number of prey consumed per time step. We'll talk more about functional responses in a little bit, but I just wanted to introduce that. And then the predator population growth model. Now, you'll see this negative QP term with an asterisk to represent possible density-dependent other types of population growth models. Now, in the absence of prey, V, this functional response necessarily has to be 0 because that's the prey consumed per time step, per predator. And that obviously has to be 0 if the prey population is 0. There can't be any prey consumption. Therefore, this whole term becomes 0. And this negative QP term represents the growth of the predator population in the absence of prey. Now, why is it negative? Well, what do we expect the population growth rate of the predators to be in the absence of prey? Negative, right? So we just make that explicit here, that in the absence of prey, the predator population growth is negative and growing maybe exponentially at a rate of negative Q. And I put the asterisk here just to represent the fact that we might make the model more complex for the predator population growth in the absence of prey if we so choose. All right, and this term here is just the functional response. That's the number of prey consumed per predator per time step. And if we multiply that by the total number of predators, we get the number of victims consumed. But we have to multiply that by a conversion factor if we want to convert the number of victims consumed into the number of new predators produced. That is the conversion of victim biomass or prey biomass into the production of new predators. That term here, this functional response times the conversion factor, is known as the numerical response, and that's the degree to which the predator growth rate is increased for each new victim that it consumes. So to differentiate the numerical response from the functional response, the notation is often changed. The F of the functional response is changed to a G, and so this functional response times the conversion factor is often represented as this function G, which is a function of the total number of victims and potentially the total number of predators. So that's the numerical response. So you should know what a functional response is. That's the per capita rate of prey consumption per predator, and that's also per time step. And the numerical response is the degree to which the per capita rate of predator population growth increases due to prey consumption or for each prey consumed. There are many different types of functional responses and numerical response curves, and we'll go through some more complex examples at the very, very end of the lecture. But let's first get familiar with the most basic prey-predator population model, and that is known as the Lotka-Volterra prey-predator model. Just like we went through the Lotka-Volterra competition model earlier, we're going through the Lotka-Volterra prey-predator model. So let's think about the simplest possible interaction of prey and predators. We'll consider the victims first. In the absence of predators, we'll assume that the victim population grows according to basic exponential growth. So the change in the victim population is equal to the intrinsic rate of growth, R, times the victim abundance. We'll assume that growth rate is positive. That is, in the absence of predators, the population grows exponentially, does not decline. If predators are present, the population growth of the victims will slow down because they're being eaten. And we have to define the rate at which prey are consumed by predators. We have to define the functional response. All right. So let's first, in a very, very simple way, assume that predators and prey are just bumbling through their daily existence without really paying any attention, and they just bump randomly into prey. And the prey are, again, just wandering randomly through the environment and just happen upon predators every now and then. So this is a very passive model of prey-predator interaction, and it's simple, and it's obviously not too realistic, but it's a good starting place, and this is what the Lotka-Volterra model assumes. We can think of prey and predator in this system as like molecules in a solution, or molecules moving through the air, occasionally bumping into other molecules, and when they do, there's a reaction potentially. In just the same way, prey and predator may bump into each other, and when they do, the predator consumes the prey. We're making some pretty big assumptions here. We're assuming that the predators are not interfering with one another, that predators are maintaining territories or whatever. And we also assume that the predators never get full. They can eat as many prey as they bump into. It doesn't really matter. Like, they can't get satiated. And each predator consumes a fixed number of prey in a given time period. And that means that no matter how many predators are around, they're not interacting with each other. They'll bump into prey at the same rate, regardless of whether there's one predator or there's 1,000 predators. It doesn't really matter. They'll still bump into the same number of prey. Therefore, the predators, the per predator rate of consumption, which is the functional response, essentially is constant. All right. So we'll consider a simple case where there are V prey, there are V victims, and only one predator in a hypothetical system. All right. So we can even put a number on V. Let's assume there's 100 prey and only one predator. A total of 3 prey are consumed in a single day. You have 100 prey, 1 predator, 3 prey are consumed in a day. That means that 3 out of 100 prey are consumed per predator, right? Now, we can assign that rate a constant, alpha. In this case, 3% of prey are encountered by predators and consumed by the predator each day. If there were 1,000 prey in the landscape, that predator could catch 30 prey, right? Still, 3% of 1,000 is 30. So that predator would consume 30 prey. Because there's more prey in the landscape, there's more chance of bumping into one randomly. And if there were 1 million prey, the predator would catch and consume 300,000 prey per day. Now, is that realistic? No. Why is that not realistic? Well, a predator can only consume so much before it gets full, right? So it's kind of rate limited there. So we'll talk more about making that more realistic, but that's what the Lotka-Volterra model assumes. Given that, we have this really simple functional response. That is, for this one predator, it consumes 3% of the prey per day, right? So the functional response is whatever the number of victims is, 100 times 0.03 is equal to 3. That is 3 prey consumed per predator per time step. So that's the functional response. If V is bigger, there's more prey consumed per predator, right? So the functional response is just the total prey eaten per predator per time step, and it's just a function of the victim abundance. The more victims are consumed per time step per predator, right? So this is the simplest functional response you can possibly get. It's just a straight line, and the more victims, the more per capita consumption per predator. All right. And it gets to unrealistic, crazy places pretty quickly, but it's a good starting place. So first of all, let's just note the intercept. If victim abundance is 0, what's the total prey consumption rate? It has to be 0. So this linear relationship has to go through the 0 point in this Cartesian coordinate system, and then the function is just alpha times v. All right. Just a simple line. So alpha is kind of the slope of this line, and the line has to go through the intercept. Of course, this alpha term has a different meaning from the alpha in the Lotka-Volterra competition models that we did last week. I'm sorry about that. It's just the way the notation is, and we just have to be cognizant that the alpha term is different. It means something different in this model than it does in the competition models. So let's consider the case where there's more than one predator. In fact, there are P predators in the landscape, and there are V prey. That's making this model more general. Recall that each predator has no influence on the consumption rate of other predators. So the predators are just like molecules randomly bumping into prey, and the total rate of predation then just is multiplied. You just multiply the functional response, alpha times V, times the total number of predators to get the total number of prey consumed, because this is the prey consumed per predator. Multiply that by the total predators, and that gives you the total prey consumed per time step. That is a key thing that we need to include then in the delta V equation, right? So if we were to look at the growth of the victim or prey population, we can say, well, per time step, it grows at this exponential rate in the absence of predation, and then you have to subtract all the victims or prey that were consumed by predators in that time step. All right, and that's the full model for the Lotka-Volterra prey-predator model for describing the population growth of the prey. All right, and we'll get to the predators in one sec. One more note about the alpha term. It's also known as capture efficiency. So it makes sense in this way. Like if you think of a case where every predator bumps into all the prey in the landscape each time step, but only consumes 3% of those prey, what if the predator that consumes 50% of those prey per time step? Alpha is obviously going to go way up. That predator is more efficient in capturing. So if we imagine that every predator is kind of bumping into every prey, sometimes they're not successful in capturing that prey. We can think of alpha in this way as kind of a prey capture efficiency per predator. So just note that that's kind of a way that people like to think about this alpha term in the Lotka-Volterra prey-predator models. Let's think about predators. So we've now gone through the basic population growth models for the victims. Let's think about the other half of the predator population growth model, that is the predators. So first of all, in the absence of prey, we have to assume that the predator population will grow how we think it would grow, badly. In the absence of food, the predators are not going to do very well. So it's going to be negative growth, and we use this term Q to represent the degree to which the growth is negative. The larger the Q term, the stronger the exponential decline of the predator population in the absence of prey. If enough prey are present, the population growth of the predators will go up on the basis of that numerical response that we talked about earlier. So if we're thinking about this simple interaction where predators and prey are walking randomly through this common environment, bumping into each other randomly, each predator consuming a fixed percentage of the prey population, we recall the functional response is just alpha times V. Alpha times V being the number of victims consumed per predator per time step. That's the functional response. We have to convert that into a numerical response in order to think about how that affects the growth of the predator population. So the numerical response we can often think about as just taking that functional response and multiplying it by some conversion factor. And that takes, the functional response is in units of victims consumed. Let's convert that into units of predator population growth. All right, how much those new victims that were eaten, how much of those can be converted into making and improving the growth rate of the predator population? That's the numerical response. And the simplest way to think about that or model it is to take this simple functional response and just multiply that by a constant. This gamma constant can be called the conversion efficiency, and it's just the degree to which the prey consumed can be converted into growth of the predator population. But note that alpha is a constant, gamma is a constant. You multiply two constants together, well, that's just another constant. So the more simple way to think about this numerical response is just to say, okay, G of V, that is the numerical response, or the degree to which the population growth rate of predators is increased for every victim consumed, is just equal to this beta constant times V, or the number of victims or prey in the landscape. That's the numerical response. All right. So what's the shape of the numerical response? Well, it looks exactly the same shape as the functional response. The more victims, and again, it's just a function of the victim abundance here. It's not a function of the predator abundance as well. There's no interference. The predators are not interfering with each other. So it's just a matter of victim abundance. The more victims consumed, and the more the predator population can grow now. And this is the numerical response. You see the numerical response just is a way to represent the increase in the growth rate of the predator population per time step as a function of the victim abundance. The more victims, the more the increase in the growth rate of the predator population, right? And the slope of this relationship just indicates the conversion efficiency, essentially, of like how much victims does it take to produce new predators and increase the growth rate of the predator population. Does the intercept have to be 0? Indeed, it does have to be 0. At 0 victims, there's no victim consumption, and therefore there can be no increase in the predator population due to consumption of prey. The increase in the total predators due to prey consumption now, all we have to do is take that numerical response, which is per capita or per predator, and multiply that by the total number of predators, and that gives you the total number of predators added to the population due to prey consumption. All right? So this whole term represents the number of new predators added to the population each year or time step due to the consumption of prey. So you can ask the question, what are the units of beta? Just like you can ask the question, what are the units of alpha? And I didn't mention this earlier, but there is a top hat question that asks you, what are the units of alpha in the functional response in the Lotka-Volterra prey-predator model? So when you have a moment, you might want to pause the video and answer that question on top hat. All right, so we can now add this term, this beta times V times P term, to this negative Q times P, right? This is the number of new predators added due to prey consumption. This is the loss of predators in the absence of prey, right? And so you can put those together. This sort of represents the natural rate of mortality of the predator population, and then we can just add this extra growth on that is due to prey consumption, and that gives you the total growth of the predator population. So we now have an equation for the growth of the prey population, delta V, and we have an equation for the growth of the predator population, delta P. And this, taken together, is the Lotka-Volterra prey-predator model. It's pretty simple. Hopefully that makes some sense. We'll have a chance to go through this in Insight Maker, and then we'll have a chance to go through this thinking about the phase plane, which we introduced in the competition lecture. And the phase plane, just like in the competition lecture, the phase plane has a lot to say, a lot to tell us. It's a great way to really understand the dynamics of these, getting to be complex systems now with two different species. So we'll go through that in the next segment. Before we end, the term beta, is often thought of as kind of a conversion efficiency of the predator. It's not directly the conversion efficiency, really. That's the gamma term up here. That's directly the actual conversion of predators, prey into predators. But beta is often known. It relates to the conversion efficiency of the predator. It is how efficiently the predator converts his food into the production of new predators. And we can think about a case where every predator consumes 100 prey per time step. So that is, this functional response is equal to 100 here. If a certain level of victims, but the predator population growth increases by only 1% relative to a scenario with no prey. Now, consider a predator that consumes 1 prey per time step, and the growth increases by 0.1. Both are plausible. Which predator of those two is more efficient at converting prey into new predators? Well, clearly that second one is way more efficient. It consumes fewer prey, and it does more with those fewer prey. For every prey, growth increases by 0.1. The growth of the predator population. So that's just another way to think about that beta term. Let's think about these models in a different way by going into Insight Maker. I'm going to stop this, and when I come back, we will load up the Insight Maker model and run through it.